All right, number 58. And for those of you that have already done it and thought you did it correctly, the answer is E. If f of 0 equals f prime of 0 equals f double prime of 0 equals 0, which of the following must be true? Now they italicize those words to help you see that those are important words in standardized test questions. In all likelihood, any actual standardized test would not italicize those for you. That really matters. Well, first of all, when is something not true? And this is a mathematical thing you should have learned in geometry. Well, that's not a mathematical interpretation. Because that's hard. Okay, that's technically not wrong, but the problem is that mathematically speaking, how do you prove that something's not true? Well, I mean, you could write a proof. There's a variety of proofs. You could write paragraph proofs. You could do proof by induction, which is what Kayla was getting me to help her with. I point to the board because we were working on the board on it. The most powerful technique, and you should have learned this in geometry, what is the most powerful technique for proving a statement false? Counterexample, ring a bell? If you can think of one instance where something is not true, it's not true. And that's all you have to do is say, this is false because, and then you give a counterexample. You see what I'm saying? Look at how elegant that is. And elegant mathematically means concise and to the point and gets the job done. You don't want to, that's why I get on y'all about having nasty, god-awful pages of crap on your, nobody wants to see that. You look like a very untrained math student when you do that. What must be true? Well, I wouldn't read the answer choices. I'd think about what this statement says. So the fact that f of 0 equals 0 tells me what? And here's what I would do. If I were doing this problem and I couldn't think, oh no, some of y'all would say you can think without it and then you get the wrong answer. So, but here's what I would do. I'd say, okay, well, I'm going to take this graph that I'm going to sketch and I'm going to mark it with everything I know. All right, well, if f of 0 is 0, I know what? That there is a point at the origin. This function is defined at 0 to be 0. I know that the point 0, 0 is on the graph of f, right? That was a painful pause. With so little response, all right? And then we go to our first derivative. What is the significance of the fact that the first derivative is 0? Is it, we have a horizontal tangent there, but does that guarantee me a max or a min? And I would offer you your dangram from this quiz question as evidence, right? Because didn't we on our dangram, what did we see at 3? What at 3? That my first derivative did not change sign there, right? And I don't remember who I was talking to, but somebody last week, I think it was asking me this very same question. And I said, we haven't had a lot of those yet because you were being taught how to recognize them when they showed up. So probably 99%, maybe that's an exaggeration, of the dangrams you did, there was a sign change at every number you had to find, right? Okay. Well, they being the authors of this textbook, were intentionally saving number 4 from your quiz, ones like that, and you should have seen some of those in 5.3. But again, that assumes that all those 5.3s in my basket were mostly done before you took the quiz. That's the other problem with lagging behind, is that you get slapped in the face with a quiz, and I'm less empathetic when you want to come back and retake the quiz. So what did we discover? That I can have a critical number at which the sign does not change, right? Because for a critical number to be a max or a min, what has to happen there? A sign change in the first derivative. Does that make sense? Okay. So I have to have a sign change in the first derivative. So the fact that I have a slope of 0 means one of 3 things. It means that there is a what at 0? It guarantees me a horizontal tangent at 0, right? Okay, but it could be a max, it could be a min, it being 0, or nothing in the context of maxes and mins, right? It could be neither. So the fact that it could be neither doesn't promise me anything. Does that make sense? Okay, well then we get to our f double prime equals 0. What happens when f double prime equals 0? You have a possible inflection point, right? Okay, so then we start looking at our answer choices. So A says there is a local maximum of f at the origin. We don't have enough information to decide that, right? Throw A out. Then, but see how thinking about this makes these a lot easier to interpret? B says there's a local minimum. If I can't say it's a max, I can't say it's a min, right? So it's kind of like 2 for the price of 1 there. Now I'm down to 3 choices. C says there is no local extremum of f at the origin. What does that mean? There's no max and there's no min. Can I say that? Not without more information. All right, then I'm down to I've taken what was a 1 in 5 shot and narrowed it down to a 1 in 2 shot. If you can do that on any multiple choice question on any test, you should jump on the guess if that's all you have left. But D says there is a point of inflection of the graph of f at the origin. There's a great possibility that there's either A or B and or D, right? But it's just a possibility. I don't have enough information to be definitive about it. So then when I read E, there is a horizontal tangent to the graph of f at the origin. And here's what happens when you do these problems. And and quick show of hands, I want you to tell me if this happened when you tried to do this problem. But you got it right. So you went through A, B, C, and D, and when the answer is E, I'm starting to get nervous. Because I'm thinking, oh, I must not be thinking right about something. But then when I read E, I know that for a fact. Do you see what I'm saying? And suddenly I'm like, oh, well, that feels so much better. Does that make sense? So that's really what you need to get to the point where you do, is that you think it through before you read the choices so the choices don't trip you up. Because all those magic words like maximum, minimum, extrema, inflection point, etc., all those are going to pop up. So only write what you know for a fact on ones that say things like that. Now let's look at 59. 59 says the x-coordinates of the points of inflection of the graph of R. Okay, so here's our function. We have y equals x to the 5th minus 5x to the 4th plus 3x plus 7. All right, so if I want to know points of inflection, what do I have to have? Second derivative. If this is a multiple choice question, I am not looking for you to impress me on your first derivative. In other words, if it's factorable, you may or may not need to factor it, because factoring it may or may not do you any good at all if all they're asking you for is a point of inflection. So let's go ahead and find those. So my y prime would be, and I need to hear lots of voices when I ask you something that we've been doing this long. 5x to the 4th minus plus 3. Looks better already, yes? Y double prime. And they give you something like a 5th degree polynomial on one like this to discourage you from trying to do more work than you need to for y prime. They being, again, the authors. All right, so what's my my second derivative? 20x cubed. 60x squared. And the zeros, the third term gives me a 0, right? So that's all. So now, pull out what you can. What do you get? 20x squared can come out of both terms. What does that leave me in the first term? X minus 3. All right? Okay, well, before we go any further, I want to also point out to you that this is a 5th degree polynomial. Why should you be able to predict what happens on it? Because it's a 5th degree polynomial, right? What's its leading coefficient? Positive 1. So what should this one act like? Right, the cubic guys, right? Which tend to climb, dip, and then climb out, right? I mean, if they're going to do something. So that should reassure you here. And we didn't have a domain restriction. So when we do our y double prime chart, and I'm not even going to do a y prime chart because I don't need it. I only want to know about the points of inflection. You see what I'm saying? And I keep bringing these things up because I have people that are going overboard in places where you don't need to be doing work, but you're still being slack in places where you need to be doing work. So trying to help you figure that out. All right, what are the zeros of my second derivative? 0 and 3. So I'm going to put 0 and 3 on my chart. All right, to the left of 0, what's true of all those numbers? They are negative. That was not a trick question. And that matters because when I look back at this thing that I've just factored, this second derivative, the first term is going to be what? Where? Always. If I notice that, I'm an idiot not to do this. I'm going to go right up under it and I'm going to put a positive in parentheses. I'm going to put a little plus sign to remind myself so that your brain doesn't do something stupid like telling me that if I plug in a negative, I get a negative, right? Why is it always positive? Positive coefficient, even power on x, right? Okay. Then we go to x minus 3. All right, well, if I put a negative number in for x, what is that going to be? Negative, making my y double prime negative there. Does that make sense? I'm going between 0 and 3. What's your favorite number there? 1. Mine too. All right, if I put 1 in for 20x squared, what am I going to get? We decided that already. That's going to be positive. So the only thing affecting my concavity sign is that second factor. Does that make sense? This is the power of factoring things. All right, so x minus 3, when I plug in 1, is negative. All right, so what do I know so far? We do not have a point of inflection at 0. Make sense? All right, so then we're going to get a number bigger than 3. We already know the first factor is positive. Maybe 4. 4 minus 3 is positive. Positive. Okay, so where's my point of inflection? 3. It's the only one I have, right? And here's what would be a beautiful thing to do. You have those wonderful calculators, and believe it or not, even if all you had is a TI-83, it's a wonderful calculator compared to what I graduated from high school with, which was no calculator. I did not own a calculator until I graduated high school, and my aunt and uncle gave me a little scientific one, and I was like so happy. It was the first calculator I ever had. So any calculator you have is amazing. You should take advantage of having it, especially if you have the latest and greatest high-tech backlit color graphs and all that. But you should graph this function. Every time you do a problem like this, if you graph the function, it should make sense relative to what you're doing. And if you graph your first and second derivative on there with it, then you're going to start making the connections between the graphs, which is a huge expectation from this point forward. Got it? Anything else? I don't want whatever that is, so I hope I don't forget that. Yes.
On like, you don't have to do, like on 29 and 30, how do you do the acceleration?
I love how your voice trails off. Like, I don't want to ask. Okay, this goes back to sort of what we were talking about on that quiz. Because you've got to sort out in your mind what they gave you and what they're asking you for, okay? So in this set of problems, it says the graph of the position function is given. Why should that give you some sense of relief? Because that's what you're used to expecting a graph to be, right, is your function. So this is the graph of the function. I'm not going to even read the rest of the question because I know what section I'm in. It's on derivatives, right? So tell me what you know about this graph. What if I said this graph is increasing everywhere? It increases on how many intervals? 2. And then this graph decreases on 2 intervals, right? So I know, what does that tell me I'm going to have for my what? I'm trying to be very vague to get you to talk about it. We have sign changes in the first derivative at 1, 2, 3 points, right? Okay. All right, and how about the second derivative? What would that relate to in this picture? Concavity. And this graph is concave down on roughly what interval?
0 to 6.
I would say maybe 1 to maybe 4, somewhere in that ballpark, right? Because for the graph to peak and then dip, there has to be a change in direction, which is going to be somewhere closer to the middle than at the dip, right? Because what's true at 6? This graph is concave up, which tells me my what would be what? Second derivative would be positive there. Do you see what I'm saying? All right? And you don't even have to do the whole picture that way. Just kind of get your brain thinking relative to this graph, especially if you've just done one where what they gave you was the derivative graph, because that's what will happen. One problem will give you the derivative graph, the next one will give you the function, the next one might give you the second derivative. Okay, so you really got to be thinking about that. All right, so at approximately what times is the particle's A velocity equal to 0? So, all right, so let's look at that. A is the velocity. Velocity equals 0. What has to be true on the graph of the function for the velocity to equal 0? I have to have a horizontal tangent, right? Okay, now in this particular picture, it does not appear that we have horizontal, well actually, there's a little bit of a trick to this one. I see 1, 2, 3, 4 horizontal tangents. Do you see them?
Yep.
Where are they? 2-ish? 6? No, that looks more like 9.5-ish to me. And at 15. Do you see that? Okay. Do you see a horizontal tangent at 0? If you were gonna extend the picture at 15, what would you probably do? You'd probably go back up because it looks like it's almost flattening out at 15, right? Because that's what would give me a horizontal tangent, right? Does it look like I'd have a horizontal tangent at 0? Because if you drew that out, what would you probably do to keep it smooth? It would drop into the third quadrant. It wouldn't bounce off the x-axis there. Does that make sense? All right. And then B says, where is the acceleration equal to 0? Okay, don't look at this graph. This is a graph of what? The function. All right, this is the position, which is the function, right? And we just looked at the first derivative, which told us something about where our tangents were equal to 0, or our horizontal tangents were. Okay, now we want to know about our acceleration, which is what? Which relates to what we were talking about graphically? Concavity. Okay, so acceleration equal to 0, right, where the concavity changes, right? Which is kind of related to what I asked you a few minutes ago. So tell me now, roughly where would that happen?
Around 4.
At about 4, 8, and 11. And we'd be speculating about concavity changes back towards 0.
And you're just sort of guessing.
Yeah. You'll never be able to read unless they explicitly mark points and tell you all the points marked are locations where the first or second derivative equals 0, and they would leave that for you to interpret, but typically they don't do that. And inflection's a lot harder to just see off the graph than first derivative sign changes. Does that take care of you for?
Yes.
Okay, good. Any other lingering 5-3 questions?